To simulate a cold water tank system, we first have to choose a tank system. In the demo version of the program, two storage systems are contained. One with 2 cubic meters storing capacity and one with 4 cubic meters storing capacity. I will take the 4 cubic meter tank for this example. If we have cold water running below 0 degrees Celsius, we have to use a mixture between water and antifreeze. This changes the density and the specific heat capacity. In the data bank, this is already programmed. We have an adapted fluid density and adapted specific heat capacity. We will run this experiment with an ATS phase change material with a phase change anywhere around minus 3 degrees Celsius. Due to the fact that we have a big tank, we take bigger objects, in this case HeatSail XL version 11.20.23. Let's start with the response test, and let's start with the first time step beginning at 0 seconds. We will bring a supply temperature to the tank with 0 degrees Celsius, and we will run the system with a mass flow of 3 kilograms per second. We will investigate the response test over 10 hours, 36,000 seconds. We won't change the supply temperature and we won't change the mass flow. The initial temperature of the tank system will be minus 6 degrees Celsius, and we change from heating case to application case cooling. The simulation shows that the tank is empty after about 8 hours and after a short time delivering very cold, sensible cold, goes over to the phase change and then goes for the next 6 hours to a normal heat exchange. Calculating the power delivery and the energy delivery of the tank, we see that after delivering very high power, anywhere around 67 kilowatt, the power decreases to anywhere between 30 to 40 kilowatt, anywhere around 35 to 38 kilowatt, stays stable over the time of the phase change and then decreases further on during the sensible heat exchange. This diagram shows that this system should be used anywhere between 30 and 40 kilowatt continuously power. Now let's set up a dynamic simulation for this cold tank. Now we have a chiller on the left hand side, which is able to regenerate our cold tank. On the right hand side, our system, which needs cold water from this tank system. So let's start at 0 seconds, and I will deliver the system a temperature of 0 degrees Celsius while the system brings back a temperature of 3 degrees Celsius. Mass flow will be 3.5 kilograms per second. That makes a delivery capacity of close to 40 kilowatts, close to 39 kilowatt. I will run the system over 72,000 seconds, that is 20 hours, close to a day, and I won't change the behavior of the system, and I will always deliver as long as possible close to 40 kilowatt. The initial tank temperature will be minus 6 degrees Celsius. I will define the usable source twice the time the normal energy need is, so in this case anywhere around 76 kilowatts. I will double the mass flow to 7 kilograms per second, and I will have a minimal temperature from minus 6 degrees Celsius. You now see the behavior of the tank system and the chiller. Here we see how long the tank system is able to deliver close to 40 kilowatt hours after 3.10 minutes the tank runs empty, must be generated, and after regenerating the tank system, we can deliver for the next time an amount of approximately 120 kilowatt hours cooling capacity to the system. This is the temperature distribution. You see that the load gets constant supply and return temperature. The storage system delivers and is generated by the source, which runs whenever the tank is out of energy. Here you see the mass flow distribution in the system between the tank, the chiller, and the process.